Okay, so just work on number 1 for now. Okay, position versus time graph. We're looking for the total distance traveled and the average velocity over the entire trip. Okay, so on a position time graph, we can read where the object is at various points in time. Okay, that allows us to see where it goes and calculate how far it travels over the course of the graph. Okay, it also allows us to calculate its displacement. Okay, how much does it change its position and in what direction? Also allows us to calculate speed and velocity because we have position and time on the graph, and velocity is displacement over time and speed is distance over time. Okay, so on this graph we're asked to calculate the total distance traveled. Is distance vector or scalar? It's scalar, so it doesn't care which direction it goes, just how far. All right, so for distance, we got to figure out how far it goes in each section. So in this first section here, okay, we start at a position of 0 and end at a position of -6 meters. So we go -6 meters during that section. What does it do during the next little bit here? What's it doing here, guys? Nothing. It's not moving at all. Its position is staying at -6 meters. It isn't moving. Okay? Then it goes from -6 meters to +6 meters. That would be +12 meters. Okay? And then it goes from 6 meters down to 2 meters. So that would be -4 meters. Now I put the positives and negatives in there just because it's always a good idea to do that. Do I need the positives and negatives to calculate distance? I don't. I just need to take all those numbers and do what with them? Add them together. 22 meters. Okay, 6 plus 12 is 18, plus 4 is 22. Okay, so our total distance traveled, 22 meters. Ringing a bell? Okay. Now, we need to calculate the average velocity over the whole trip. Our formula for average velocity is that it is the total displacement divided by the total time. And we can calculate displacement by taking final position and subtracting initial position and then dividing by time. Okay, we have all of those numbers on the graph. Our final position on this graph, okay, is +2 meters. Our initial position on this graph is 0. Okay, this whole thing takes 20 seconds. All right, so 2 minus 0 is 2. 2 divided by 20 is 0.10 meters per second, and I'm just going to put on there that it's positive because that's the only vector I've got. Okay, ringing a bell? All right. The one below is a velocity versus time graph. Okay, the x-axis is up here at the very top. Okay, this is 0. Everything is negative in this one. Okay, so this object only travels downward, backward, whatever you're deciding the negative direction is going to be. Okay, just keep that in mind. I would like for you to calculate the total displacement of that object. You may have to remember some geometry to do this. So, on number 2, okay, if I want to calculate the total displacement, then I need to use the average velocity times time, because that's how we calculate displacement, okay? It's related to distance and time, or displacement, time, and velocity. So if I want to calculate displacement, I simply multiply the time over to this side. Now, I can get the average velocity and the time from this graph because those are the two things that it's showing me. During this first 2 seconds, what is the object doing? Not moving. It has a velocity of 0 meters per second, so nothing to worry about right there. Then it accelerates backwards, okay, from 0 meters per second to -9 meters per second. Okay, and it does that over what appears to be 2-3 seconds, okay, from 2 to 5 seconds. All right, so I know that the base of this is going to be 3 seconds. Okay, and I know that it accelerates from 0 to -9. All right, well, if it accelerated from 0 to -9, the average, well, is halfway between 0 and 9. Okay, so I'm going to take half the height, base times height over 2. Okay, that gets me the average velocity. So 3 times -4.5, 13.5. Is that right? -13.5. I should probably start at the calculator. Okay, and then we've got this rectangle right here where the object travels at a constant speed of -9 meters, constant velocity of -9 meters per second for another 2 seconds. So that would be another -18 meters. Okay, what do I have to do with those two numbers? Add them up. Okay, so my total displacement here is going to be -31.5 meters, if my mental math is correct. Okay, everybody with me on that? I wouldn't expect anything like radically more difficult than that as a unit exam question. I just need to know that you know how to do it. Not that you can calculate the area of 9 different shapes in a short period of time. I'm not testing speed, okay? I'm testing how well you know how to do it. Okay? Questions on that? Okay, let's try number 1 there. See how we do with that. See what we remember from before the break. Okay. What kind of question is number 1? Let's walk through the given, see if we can figure it out. Okay, so I got a small cart. It has a mass of 1.5 kilograms. Okay, and there's a force acting on it. That force is 85 newtons. Okay, and it causes it to accelerate from an initial speed of 1.3 meters per second to a final speed of 2.1 meters per second. Okay, it wants me to calculate the distance over which the force is accelerating the cart. Now, if something accelerates, is its energy changing? What kind of energy? Its kinetic energy is changing. Okay, the only way you can change energy is by doing work. Okay, so this is a work energy theorem question. Okay, work in this question is changing the kinetic energy of the cart. Okay, we know we can calculate work by multiplying force and distance. I have force. Question wants me to solve for distance. And change in energy is is final minus initial. So that would be like 1/2 mv final squared, my final kinetic energy, minus 1/2 mv initial squared. Everybody okay with what I've set up there? Okay, how do I get D? I've got to move F to the other side. Right now I'm multiplying F, so to move it to the other side, I would divide both sides by F. Now all I got to do is plug in my numbers and solve. Okay, so D is going to be 1/2 times 1.5 kilograms times 2.1 meters per second, all squared, minus 1/2 times 1.5 kilograms times 1.3 meters per second. Oh, I won't put the units in there. And that number will be squared. And then I'm going to divide all of that by the force, which was 85. I'll make that look like 5. 85 newtons. Okay, so that will get me the distance traveled. So in my calculator, that's just going to look like this. 0.5 times 1.5 times 2.1 squared minus 0.5 times 1.5 times 1.3 squared. Okay, now divide that by 85. Okay, is that very far? 2.4 centimeters, 0.024 meters. That's not an unreasonable answer. 85 newtons is a lot of force for a small cart. Okay, and we didn't change its speed by that much. Okay, so it really didn't take that much work, okay, in order to do this. We only used 2.04 joules worth of work here. Okay, that's not a lot of energy. Okay. All right, so 0.024 meters, okay, would be our final answer. All right, ringing a bell? Okay. Let's have to try number 2. Okay, just in case anybody's stuck. What kind of question is this? Is this a work energy theorem question, or is it a conservation of energy question?
Conservation of energy.
It's a conservation of energy question. Here's how we know that. First, no force is given nor asked for. Second, his energy doesn't change. At least not the total amount of it. The type of it does. When he's in the middle there on the bottom, okay, what's his energy? What kind of energy does he have there? That's weird. What kind of energy does he have at the bottom there? He only has kinetic, right? Because he's on the ground. His height is 0 in the middle of the half pipe. He can't fall through it, right? So he can't go any lower. So if I'm looking at that, okay, his initial height is 0 meters. And his initial speed is 12 meters per second. How fast is he going here at his highest point? 0. Right? When you throw something up in the air, when it gets to its maximum height, it stops for an instant before it falls back down. So up here, no speed. And this is where they want me to calculate, sorry, that should be F, okay? His height. Okay? No work is being done here. The height he reaches there is entirely due to the kinetic energy he has in the middle. Okay, so this is one of those EI equals EF questions. All right, so if you were stuck or you're trying to solve it the wrong way, okay, I'll give you a couple more minutes here to see if you can solve it using the law of conservation of energy, and we'll talk it through. Okay, let's walk through the rest of this one together. So, to let you know before we started, mathematically, this is one of the easiest ones you can get, mathematically. Contextually, this is one of the toughest ones you can get, because it relies on you to be able to read the story, look at the picture, and figure this part out, okay? To figure out that, oh, when he's at the bottom, his height is 0, and he only has what kind of energy? Kinetic. Whereas up here, his velocity or speed would be 0, and he would only have what kind of energy? Potential. That's the hard part of that question. That's what actually makes this a harder question than one where you would have all 4 kinds of energy, but it would be really obvious. Okay? This one involves you having to think and process quite a bit more. That's why I make it a mathematically easier question. Okay? So, here's what we know. No work is being done. His energy, his mechanical energy, is not changing. So we can say his initial mechanical and his final mechanical are equal. Okay, we calculate mechanical energy by adding together an object's kinetic and potential energies. Okay, like so. Now, we've already identified that initially he doesn't have any potential because his height is 0. And at the end, he has no kinetic because his speed is 0. Which leaves us with his initial kinetic equals his final potential. Okay, so that means 1/2 mv initial squared equals m times g times his final height. Okay, this is the part where the math is much easier than some of the ones we did before Christmas. I want to isolate HF. What should I do?
Divide mg.
Right, and what's going to happen to m when I do that?
It's going to cancel.
It's going to cancel, yeah. Okay, so if I divide both sides by m times g, okay, m will cancel. Would have canceled anyway, it was in every term. Okay, now I'm solving for HF. All I have to do is plug in my numbers. So 1/2 times 12 squared, there's my kinetic on top, divided by 9.81 on the bottom. That'll tell me how high he would get, okay, as a result of this. So 0.5 times 12 squared, okay, divided by 9.81. Okay, so he is going to be 7.34 meters above the lowest point, or the ground, okay, when he reaches his maximum height. Okay, is that ringing a bell? All right, let's try one more here. Let's try that one. Then we'll talk about efficiency. If we have time, we'll do another. Okay? Is this one also a law of conservation of energy question? Yes. Okay, how do we know that? There's no force, right? There's no force mentioned here, and there's nothing to change the mechanical energy. Gravity doesn't change mechanical energy. Gravity just turns it from potential into kinetic. Okay, so the energy, the mechanical energy of the person on the sled is not changing in this question because no work is being done. Okay, so we can safely say that their energy here and their energy down here are the same. Okay, everyone all right with that? All right, what are our givens? Well, we know that when they're at the top of the hill, they're moving at 6 meters per second. And they are 35 meters above the bottom of the hill. The other position we're asked about is the bottom of the hill. What's my final height? 0, because I'm at the bottom. Okay, they want to know how fast are they going at the bottom. Everyone okay with that? Okay, these are the questions you kind of ask yourself as you're going through these step by step. Okay, so mechanical energy initial equals mechanical energy final. So that's initial potential plus initial kinetic equals final potential plus final kinetic. Okay, everyone okay with that? All right, are any of those 0? Scott, you're nodding your head yes, which one? Right, final potential is 0 because our height at the bottom is 0. We don't have any potential anymore. We're already down as far as we can go. Okay, so they want me to calculate VF. That would be part of this term, which now, thanks to the fact I have no final potential, is already isolated. Can I plug in my formulas now? Okay. All right, so M times G times H initial plus 1/2 mv initial squared equals 1/2 mv final squared. Okay, what were you not told about this sledder? Their mass. Does it matter? No, it doesn't. Okay? It wouldn't matter how big an object was sitting on that sled, they'd be going the same speed when they got to the bottom. Okay? Only gravity is working here. Okay? So I can take off all of the masses. So we'll just cross them. All right, so I'm going to cross off all the m's, okay, and I just need to isolate VF. So what do I have to do with this 1/2? Divide it over to the other side. Now that solves for VF squared. What do I want? just VF. So what do I have to do? Square root. Okay, so this one a little more mathy, but a little less contextually challenging. All right, so I'm plugging in my numbers here. Okay, I've got 9.81 times 35 meters, my initial potential, plus 1/2 times 6 squared, my initial kinetic, divided by 1/2. Okay, so looks like when he gets to the bottom, he better be wearing a helmet because that's fast. Okay, if he has to bail out, he's gonna roll a ways and he might get injured because 26.88 is 96 kilometers an hour, almost 97 kilometers an hour. So like bobsled kind of territory. Okay, he's doing the cool runnings thing. Okay, everyone all right with that one? Okay, those are the kind of things that are going to be on the test on Thursday. Okay, the trick is, can I identify that this one is conservation of energy, this one is work energy? Okay, how do I get, you know, the displacement from this kind of graph or that kind of graph? Those are the things I'm going to ask you to do. Okay, let's talk about efficiency here. Okay, what is efficiency? When something's done efficiently, what does that mean? Carter, what's more efficient? Your truck or a little like Honda Civic?
Honda Civic.
Why?
Because it uses less gasoline.
Right. It uses less energy to do similar tasks, let's say. It's obviously not going to be able to do all the tasks that a big truck does, okay? But it can do most of them. That is, get the vehicle up to 110 kilometers an hour on the highway. Okay, now obviously a Honda Civic is a lot smaller, okay, but that's part of why it's more efficient. Okay, efficiency has to do with you have this much work to do. Okay, how much energy do you actually use to do it? Okay, we've dealt with up to this point everything being 100% efficient. No energy is wasted anywhere. Is that how things work in the real world? Absolutely not. Energy is wasted everywhere. We want to make things more efficient, okay? Not have wasted energies, because that makes us better stewards of our resources and the environment and all of that kind of important stuff. It's why, for example, okay, we use LED lights to light this room. Okay? I mean, I'm old enough because, we used to use candles. When I was a kid, not that old, but okay, our light bulbs when I was a kid were the tungsten filament kind. Okay, the Thomas Edison invented ones that had the metal little coil inside of them. Okay, those kind of light bulbs, they're called incandescent for a reason. Incandescent means to make light from heat. Okay, so what would happen when you flipped on the light switch, okay, and you had a tungsten filament bulb? Tungsten is a terrible conductor of electricity. So as the electrons try to go through that filament, they get slowed down. Okay? And when they get slowed down, they give off their kinetic energy as heat. And that little tungsten filament would get really, really hot, almost immediately. Okay? And it would glow white hot as long as you had electricity going through it. Okay? One of those little bulbs would take 60 joules of energy every second to run. Okay? Now, we replaced those with LEDs. Okay? I can now put in an LED light bulb into the same socket, and that LED bulb only uses 4 joules of electricity per second. Does that make it more efficient? Yeah, because it's doing exactly the same job. It's lighting up the room. It's providing X number of lumens of light, okay, every second, and keeping me from being in the dark where I would be cold and scared, right? But it's doing it way more efficiently. Okay, like I can actually remember when I took all the tungsten filament bulbs out of my house and replaced them, okay, with, well, at that time it was the little coiled compact fluorescent bulbs. My electricity bill was almost cut in half because I went from having 60-watt bulbs to 13-watt bulbs. Okay, they used 1/4 of the electricity, okay, that the old bulbs used and did the same job. And then when I dropped down from there, okay, I went down and got bulbs that used 1/4 of the electricity of the compact fluorescent. Okay, a 4-watt bulb does the same work, okay, does the same job, okay, but it's more efficient. Everybody follow me there? Okay, we want to be efficient because we want to use less energy. Okay, so let's look at some examples here. Okay, so the purpose of any machine is to convert the energy you put into it into useful work output, whatever the job of that machine is. Okay, if it's your hair dryer, it's to blow hot air, okay, and dry your hair. If it's your toaster, it's to emit heat and cook your bread. Okay, whatever the job is. Okay, we want to make as much of the energy that goes into that machine do that job as possible with minimal waste. Okay? Now, I would assume most of you arrived here in some sort of vehicle today, yes? Okay, how many of you arrived by bus? Okay, so all of you took a vehicle that runs on internal combustion, okay? Burns fuel, gas or diesel, okay, to get here. Anybody arrive here this morning in a hybrid vehicle? I'm the only one, okay. That's all right. Anybody arrive by electric vehicle? Okay, that's all right too. Okay? What's the purpose of trying to make more vehicles electrified? No politics here, by the way. Okay? Just what's the general purpose of trying to make more vehicles have at least some electric driving component? Is it more efficient? An electric motor is more efficient at doing the same job. Okay, so if I compared, let's say, a mid-sized sedan that is just an internal combustion engine, so I don't know, like a Honda Accord, okay, or a Toyota Camry, or Ford, I can't remember what their mid-size one is called now. Okay, anyway, something with 4 doors, okay, and I put it next to a Tesla, okay. Obviously, one has gasoline power and the other has electricity. Okay? I don't get to, just because I have an electric car doesn't mean I go back and forth to work for free. I still have to pay the electric bill that charges the battery. Agreed? Okay. That's still going to save me money. The electric vehicle is going to do the job of taking me to work more efficiently than the gasoline-powered engine. Okay, as much as we might not like to hear that, okay, it is 100% true because electric motors have way less wasted energy. Okay, they don't produce nearly as much heat as an internal combustion engine. Internal combustion engine needs heat to run. That's how it works. Okay, it burns the gases, creates little explosions where that heat gets turned into mechanical energy that moves the piston up and down. Okay, but it makes way more heat than it needs, and a lot of it is just wasted. Okay, we want to look at being more efficient. One of the ways to do it is to look at how we get back and forth to work every day. All right, so if I have just a gasoline-powered vehicle, okay, I turn it on and let's say I put $100 worth of gas in it. Okay, not that hard to do these days. Okay, I put $100 worth of gas in it. Okay. The engine will lose $68 to $72 of the gas I put in as waste. Okay? It'll make you cry every time you're sitting there with the pump inside your car and the gas going in, knowing that 2/3 of the energy that you're putting into your car is just going to go out and warm the air around your car. Okay? That is going to be things like the radiator. Exhaust. You ever notice the air coming out the exhaust pipe is hot? Okay, it is. What's that doing? Nothing. Okay, it's just going out into the environment. Okay, combustion. Okay, pumping. You've got a water pump in there that's pumping coolant through your car. Why do you need coolant? Because your car gets really, really hot, and if you don't have coolant, the engine will literally melt. Okay, the pistons will expand, they'll seize, and the whole engine just breaks down. Okay, and then there's internal friction. So, okay, exhaust, heat, etc., 58 to 62% of the energy in your fuel. Okay, combustion 3%, pumping 4%, friction 3%. Okay, there's a lot of waste in internal combustion as heat. Okay, then you've got electrical losses because your car has this thing called an alternator. Okay, it's connected to the main drivetrain by a belt usually. Okay, and as your engine spins, it also turns this alternator. The alternator generates electricity. Okay, 12 volts of direct current electricity. That runs all the electrical parts of your car. Okay, so if you have things like climate control, okay, so your heater, your defogger, if you have a heated seat or heated steering wheel, okay, or anything of those really nice things, okay, your headlights are on, you got a big stereo, okay, with the subs in the back and 3 amplifiers, okay, all of that runs on electricity. Okay, and the more of those things you run, the more your engine has to work to generate the electricity to power them. Okay, I once had a student who had to put a larger, or actually a second, alternator in his car to power the stereo. Okay? He drove around in this 1992 Fox body Mustang. We called it the Rustang. Okay, it was an absolute piece of junk. But he had about $10,000 worth of stereo equipment in the thing. Okay? And he would turn it on in the parking lot and he would flick a loony onto the roof, and the loony would dance, because the stereo would pound so loudly, okay? But he had to put another alternator in to power it, because if he turned the volume up, the car would die, because it couldn't power the stereo. The power required to turn the alternator wasn't sufficient, so he had to put a second alternator in, okay? So to power all this electricity. So the more electrical stuff you have in your car, the more electricity it's going to use, okay? Parasitic losses, so just things that your car does, okay? So water, fuel, oil pumps, ignition systems, engine control, so that's like pollution control, okay? Those all result in the loss of efficiency, okay? Energy to the wheels, when you're all said and done, somewhere between 16 and 25% of the energy in your car, okay? Now you also have these things. If you have an internal combustion engine, you've got drivetrain losses and idle losses. So if you're just sitting at a stoplight and your car is idling, are you still using fuel? Is it doing anything good for you? Maybe keeping you from freezing to death. It's cold outside. Okay, but it's certainly not powering the car forward. So when all is said and done, okay, the energy to the wheels is 16 to 25%. So of the $100 worth of fuel you put in your car, only somewhere between 16 and 25 of those dollars actually makes you go. The rest is waste. Okay, is that very efficient? I mean, think of it this way. Would you go to a doctor who was only right 20% of the time? But we accept that our car only uses 20% of the energy we put in it. Okay, we accept it on a daily basis. We come to work, that's how we get here. Okay, are we making cars more efficient now? Sure, the internal combustion engine is way more efficient than it was 10 years ago, especially 20 or 25 years ago. Okay, but it's still something that's turning heat into mechanical energy. So it's not. It's going to have limitations. It's only ever going to be so efficient. All right, does that sort of make sense? Where the energy's all going? Okay, so a lot of it is lost as heat. Now, if you have a newer internal combustion engine car, some of them will actually turn the engine off when you're stopped. Okay, anybody have a car that does that? Okay, engine turns off, just automatically turns it off at a stoplight. I find that incredibly annoying. They always disable it. I'm one of those people. Okay, who doesn't care about efficiency, cares more about convenience. I can't stand it when the engine turns off. Okay, but it's a way to save energy. You can run off the battery for as long as you're going to be at a stoplight. All right, let's compare that to the same model of car, but now it's a hybrid. Okay, so what's the advantage of a hybrid? What do you have in a hybrid car that you don't have in an internal combustion car? You have a battery and an electric motor. Okay, some hybrids can run on the electric motor a little bit. Okay, my wife has a plug-in hybrid, so it can actually run as a hybrid car and as a purely electric vehicle, so she can drive on all electric for about 40 kilometers. Okay, I have a hybrid vehicle, okay, and if I'm going nice and slow through my neighborhood, the internal combustion engine will shut off and there's enough power in the electric motor for me to like creep around the neighborhood. Okay, dead silent stealth mode. Okay, that's what I call it anyway. Yeah, it's just the angels humming, okay, sound that electric cars make. So you can do that, okay? The advantage of using a hybrid powertrain is this. You don't have to have as big a motor. Okay, so if you're looking at, let's say, a big truck. Okay, so let's say you're looking at an F-150, a Ford F-150, most popular pickup truck there is. Okay, you can get that in a V8. I know, I used to have one. Okay, you can get it in a 6-cylinder, so an 8-cylinder, a 6-cylinder, a 6-cylinder hybrid, or a purely electric one, the Lightning. Okay, but as you go from the 8-cylinder to the 6-cylinder to the 6-cylinder hybrid to the purely, actually you can get a 4-banger as well, you can get a 4-cylinder, okay, that's a hybrid, and then you can go to purely electric. The size of the engine goes down because the engine doesn't have to be as big because it's going to get help from the electric motor. Okay? A hybrid car is going to give you help anytime you're doing the most work. Okay? So if you're accelerating, the electric motor is going to kick in and it's going to help the internal combustion engine. So it can generate as much power as a big motor, but not use as much fuel because it's using electricity to help instead. Okay, does that sort of make sense? Okay, so that's where the efficiency, or part of the efficiency, comes from, is you don't need as big a motor. Okay, now it is, it's different. Okay, having driven all kinds of different vehicles, I can say that driving a V8 is fun. Okay, there's just nothing that ever replaces the sound of 8 pop cans going up and down when you press the gas. Okay, but it's not nearly as sad to go to the gas station in my hybrid vehicle as it was when I was fueling the thirst of that giant, 8-cylinder engine, right? The newer vehicle, it's more efficient. Okay, it has a smaller motor because it has an electric motor that helps it out. Okay, all right. So we still have in a hybrid vehicle an internal combustion engine. So a lot of these losses are still there. The internal combustion engine is still going to lose things in the same way. But the numbers are a little smaller because the engine's a little smaller. Okay? So you still have your engine losses. You still have your parasitic losses. You still have your electrical losses. And in fact, they can be a little bit bigger because you have more electrical parts in a hybrid car. Okay? You still have your drivetrain losses. But look at the efficiency. Instead of being 16 to 25, it's 25 to 38. Here's how it does that. A, the electric motor helps. B, regenerative braking. Hybrid and electric cars use something we talked about at the beginning of this unit to help charge their batteries. Okay? When you press the brakes, okay, the brakes, there's pieces of metal that squeeze together. Creates a lot of friction that slows you down. Does friction make heat? Okay, in an internal combustion engine car, that heat just goes to the surroundings and it's gone. In a hybrid vehicle or an electric vehicle, that heat goes to a thermocouple. And that thermocouple turns the heat directly back into electricity that charges the battery. So instead of just losing all of that kinetic energy you had when you apply the brakes, now some of it goes back to charge the battery. Okay? So it recovers some of that energy. Okay? Regenerative braking can recover 5 to 9% of the energy that would be lost in an internal combustion engine. Okay? My wife's car actually has this thing in it on the dash called the brake coach. Every time I drive her car, it's like a game. It tells me how good I did in getting that energy to go back to the battery. Okay, if I just pound on the brakes and stop really quickly, I get a failing grade. It's like 35% of the energy was recovered. But if I brake nice and slow and I let that heat build up, okay, and go into the thermocouple, I can get up to 100%. Now, it's not really 100%, but it just tells me I did 100%. I did really good. And when I'm driving her car, it's all about getting that 100% number on it. Okay? Not all cars do that, but it does kind of teach you to brake efficiently, okay, and get a lot of that energy back to the battery. Okay, now, what happened to the electric? Okay, so the electric car, okay, as a pure comparison here. Okay, so an electric car is going to run 65 to 69% efficient. Okay, internal combustion engine was 16 to 25. Okay, the reason for that is the way an electric motor is built. Okay, in an electric motor there are magnets. The actual parts that move don't touch each other very much. Whereas in an internal combustion engine, metal slides past metal all the time. Okay? But in an electric motor, okay, there's very little friction. So there's very little heat. Okay? That's why they can run at this rate. But then you add in that regenerative braking, and you've got a car that's running at 87 to 91% efficiency. Do I still have to plug it in when I get home? Yes. But the amount I'll pay in electricity is a lot less than the amount I'll pay in fuel. Okay? I can speak from personal experience with my wife's plug-in hybrid that can run as an electric car. She just works here in town. Okay? That thing, we bomb around in that thing in all electric mode, do our shopping in town. We hardly ever go to the gas station. Okay? And I did the calculations. To actually charge that battery cost me about $1.05. And we can go 50 kilometers on $1.05. I sure can't do that in my internal combustion engine vehicles. Okay? It's just more efficient. Okay? Now, the environmental part of that. Okay? This is where the argument of, I want an electric car to save the environment. Where does most of our electricity come from in Alberta?
Natural gas.
Yeah, natural gas and coal. Okay, I mean, we like to kid ourselves and say, well, the wind farm down in Pincher Creek and the solar farm out at Aldersyde, they help. Yeah, they're like less than 6% of the entire electric grid in Alberta. Okay, most of Alberta's power grid is coal and natural gas being set on fire to make steam, to turn a turbine, to make electricity. Okay, so while you're putting less CO2 in the air by having an electric car, you are not removing your carbon footprint. You are still plugging into the wall and making somebody burn something, okay, to charge your car. But you're doing less. Okay? So you're doing your part, but you're not saving the environment. You're not eliminating all of your contributions to carbon dioxide, at least here. Unless you're like my neighbor. My neighbor bought a Tesla, and then he got solar panels put on his roof. His solar panels, most of the time, when they're not covered in snow, generate enough electricity to charge his Tesla. Did he remove his carbon footprint? Almost entirely. Other than the manufacturing of the solar panels, yeah. Okay, he did. I don't think he's getting ahead though, because it was a big put out of money to put the solar panels on the roof, but you know, whatever you gotta tell yourself. Okay, so efficiency, it's important. It's how much energy do we use to do a job. Okay, so here's the math of it. Efficiency is a percentage. How do you calculate what you got as a percentage on a quiz or a test? Take your score and divide by whatever the test was out of, and you got it, right? It comes out as a decimal. If you got 87%, you get 0.87. That's how efficiency works. Efficiency is just a percentage. Okay? So you take the useful work, okay, that's what was actually done, and divide it by the energy input. How much energy did you have to put in to do it? Okay, when you divide those two numbers, you'll get a decimal. That will be your percentage. If it's 0.56, you are running at 56% efficiency. Okay, if it comes out to 0.98, you are running at 98% efficiency. If it comes out to 0.1, 10% efficiency. Okay, but it's a pretty easy mathematical calculation. It's just calculating percentages. Okay. All right. Let's look at this example here, just at the end of class here to kind of see how this works. Uh-oh. sure now I've got like a whole page worth of blank. Okay, so in this example here, we've got a crane that's lifting construction materials up to the top of a building. Okay, so it takes it from the second floor, okay, and it moves it to the top. In the process, the crane does 23,000 joules of work. Okay, that's how much work it has to do. The load, the construction materials, they only gain 8,000 joules of energy. Okay, so definitely not 100% efficient, right? The crane used 24,000 joules of energy, but only did 8,000 joules worth of useful work. All right, so what's the efficiency? Well, efficiency is, okay, the useful work, which we call EM, okay, divided by the energy input, the amount of work you actually had to do. Okay, so that's going to be 8,000 joules divided by 24,000 joules. Okay, if we do that, that crane is running at 34.8% efficiency. Okay, we'll look at a little bit of that tomorrow before we do our review. Okay, you're not going to be asked to do any real rocket science calculations with this formula, guys. It's just calculating efficiency. Okay, all right, good work today, guys. Make sure you have a look over the review package here over the next few days. Hopefully your work labs are already pretty close to done.